All right, here we go. Chapter 13. So, we're going to be moving on from the basics of three-space to vector functions. So if you think about kind of our lines from last chapter and how we defined them, like think about the vector equation of a line. We had three components, and in each of those components we had a point and what kind of felt like a slope depending on a parameter t. Well, we're going to define vector functions in a very similar way, but instead of those linear seeming pieces of the vector function, we're going to allow those components to be any functions that we want. So a vector valued function, or a vector function, is going to be a function whose domain is a set of real numbers and whose range is a set of vectors. So we are going to plug in a number, and maybe I should say plug in a number into a function r, and our output is going to be a vector, which is essentially going to come from plugging in our number into three different functions and getting a vector answer. We're most interested in vector functions R, whose values are three-dimensional vectors. We can do this in other dimensions, of course, but then it doesn't have quite the same visual representation associated with it. We did this a little bit last year in BC when we got to the end of the year when we did our velocity and acceleration vectors. Those are vector valued functions only with two dimensions. So our functions that make up our three components are real valued functions called component functions. In general, if we're just notating things, we'll just call them f, g, and h. Doesn't really matter. You can call it x of t, y of t, z of t as well. That might make more sense. A lot of the things that we're going to be doing with these functions here at the beginning is going to feel familiar because it's basically just like relearning how we talked about functions in algebra or algebra 2. So let's start with the domain of our vector function, which is made up of three components, which is ln of the absolute value of t minus 1, e to the t, and the square root of t. So how you're going to find the domain for the entire vector function is you need to find the domain of the three components, and then we're going to kind of put those together. So let's go piecewise. What is the domain of ln of the absolute value of t minus 1? Because we have that absolute value, we don't have to worry about negative values being inside of the natural log, but there is one value you are not allowed to plug into a log no matter what, and that is 0. So that was a weird way to write this. I cannot write that. I'm sorry. It is ln, doesn't need to be there. The absolute value of t minus 1 cannot equal 0. So 1 is not in our domain for our first component, but it's also not going to be in the domain of the entire vector function. Let's look at the second component, e to the power t. You can plug in any number you want into e to the power t. So in that one, our domain is all real numbers. Let's look at our last component right here, which is the square root of t. We know from many years of math that our t has to be greater than or equal to 0. So to find the domain of r of t, I should notice, or you should notice, I'm sorry, that r is a vector, so I have to write a vector arrow over it. Don't forget that, please. So the domain of our vector function r of t, we're going to put all these together. So the least restrictive is all real numbers, but we have to take away all the negative values, but then we also have to take away 1. So our final domain, if I write it in interval notation, is going to be bracket 0 to 1, parentheses, unioned with 1 to infinity, both parentheses on that. Hopefully that is familiar, that makes sense. Find the domains of the components and then make the most restricted domain that you can. So let's suppose that f, g, and h are continuous real-valued functions on some interval I. Then the set C of all points x, y, z in space where x equals f of t, y equals g of t, and z equals h of t, and t varies throughout the interval I, is called a space curve. Again, we kind of did this last year, where we broke down x and y into two functions that depended on some parameter t, and then we plugged in t, and it gave us a graph, but it also gave us a direction. So think about that. We're going to have our space curves in 3D, which is going to be very similar, where we're going to have a curve in 3 space, but it's also going to have a direction to it. We're going to call that the orientation. So think of this as a path in space that is traced in a specific direction as t increases, our orientation. The equations above are called parametric equations of c, and t is called the parameter. Thus, any continuous function r defines a space curve that is traced out by the tip of the moving vector r of t as shown below. So r is some vector function based on those 3 components that are functions themselves, and then you plug in numbers and you get points that will trace out a path in space that has a direction to it. So as t increases, that is the direction our path goes. So we take that to be our orientation. So that vector function r, that blue arrow you can see right there, it is pointing towards the point that is getting traced out as a path through space. So we're going to start with something that we could have done last year, which is sketching our vector equation in 2 space. So r of t equals 2 cosine ti minus 3 sine tj. So our x is equal to our function, we'll call it f of t, I guess, 2 cosine of t, where y coordinates come from our function g of t, which is in this case negative 3 sine of t. So how do you sketch out these paths in space? Well, plug in different values of t. Many times we will have domains, sometimes we will not, but we have a domain right here for t, which is 0 to 2 pi, so we're going to make a table. It's based on our t values, and those t values are going to solve for values of x and y. Just to make this pretty straightforward, I'm going to plug in values for t that are 0, pi over 2, pi, 3 pi over 2, and 2 pi. When we plug in 0 in for t, 2 cosine of 0 is 2, negative 3 sine of 0 is 0. 2 cosine of pi over 2 is 0, negative 3 sine of pi over 2 is negative 3. Plugging in pi, 2 cosine of pi is going to be negative 2, negative 3 sine of pi is going to be 0. 3 pi over 2, so 2 cosine of 3 pi over 2 is going to be 0, negative 3 sine of 3 pi over 2 is going to be positive 3, and then finally 2 pi is going to match us plugging in 0. It's going to give us 2 and 0 for x and y respectively. Now, when you sketch this, you got to make sure you're indicating a direction. So our first point is 2 comma 0. We're moving up to 0, or excuse me, we're moving down to 0, negative 3. Now, if you recognize this, you probably don't from our parametric things. And if I were to graph a few more points in between, this is not going to be a line connecting them. It is going to be curved like this, and it is going in the direction that is what we call clockwise for this one. The next point we go to is negative 2, 0. And you might be able to start seeing the shape being formed here. Don't forget your direction that we're going to mark for our path. After that, it's going to move up to 0, 3. And I'm going to indicate my direction of travel right there. And then finally, we go back to 2, 0. And this is an ellipse. That is an ellipse. So if you're defining x and y with sines and cosines that have different coefficients in front of them, you're going to get an ellipse. And this one only goes around the ellipse one time. because of the domain restriction. We're going to go clockwise from 2, 0 around back to 2, 0, but we're only going to travel once because of that domain restriction. All right, let's look at a space curve in 3 dimensions, the more interesting stuff. So based on what I said, you might be able to tell kind of what the x and y kind of might give you a visual of. But now we have a third component where z is going to be equal to some t. So some things to notice right now. If you think about x and y as being cosine of t and sine of t, well, x squared plus y squared is going to be cosine squared of t plus sine squared of t, which we all know is equal to 1. So that kind of makes us think about this graph in 2 space. X squared plus y squared equals 1. What is that going to be? So our curve is going to lie. So curve lies on the circular cylinder. X squared plus y squared equals 1. So I'm not just calling it a circle because we have a third dimension now. But remember, if we were to graph x squared plus y squared equals 1, that is going to be our 3-dimensional cylinder in the z direction. So our curve is going to lie on that cylinder surface. Now, what does the curve look like, though? Since z equals t, our curve is going to spiral. So our curve spirals upward around the cylinder as t increases. So if you want a little bit more detail on this, you can always make a table. So I'm going to have a t, an x, a y, and I need a z this time. So if I plug in those same values that I did on the previous problem, I'm going to do this a little bit quicker here. That's going to be 1, 0, 0. It's going to be 0, 1, pi over 2. It's going to be negative 1, 0, pi, 0, negative 1, 3 pi over 2, and then 1, 0, 2 pi. So you'll notice now with our z component, that is getting higher and higher every single time. So if I were to think about what the cylinder looks like, so we have this surface right here where our cylinder is. Our first point is going to be at 1, 0, 0 right there, but our next point is going to be traveling, if we're kind of looking down the barrel of the cylinder from above, you might think about this as going counterclockwise. We're going to start moving upwards. So our next point, 0, 1, pi over 2. Pi over 2 is a little bit more than 1. It's going to be maybe here-ish, and we're going to be going around the side of the cylinder, traveling upwards. And then negative 1, 0, pi, so back at the back end, we're going to be a little bit higher up. And then we're going to keep on going. So from here on out, I'm not going to try to graph these points specifically because they might not look so good, but we get this idea that this thing is traveling around the outside of that cylinder. I'm trying to draw little dotted lines to say it's kind of going around the back of what we're imagining the surface of the cylinder to be. Now, I'm going to put arrows on this whole thing because our domain isn't restricted for this one, so this curve is going to keep spiraling up forever. We do call this type of space curve a helix. So if I were to try to draw it kind of freehand like that, that's kind of what we're doing right there. It's going to keep going up and up and up. Right. Let's move it on. Our next example, we're going to find a vector equation and parametric equations for the line segment that joins the points. We've done this before. We talked about this already. I gave you a shortcut